Friends, I am Dr. Sashikant Tamrakar from Bharatiya College of Agricultural Engineering, Durg. I will teach theory of machine of BTech first year second semester class.
Dear students, next topic is velocity in slider crank mechanism. In the previous article, we have discussed the relative velocity method for the velocity of any point on a link whose direction of motion and velocity of some other point on the same link is known. The same method may also be applied for velocities in a slider crank mechanism. A slider crank mechanism shown in figure 7.5a, I'll show later. The slider A is attached to the connecting rod AB. Let us the radius of crank OB be R, and it rotates in clockwise direction about the point O with uniform angular velocity. Here the slider A is attached to the connecting rod AB. Let the radius of crank OB be R, and let it rotate in a clockwise direction about the point O with uniform angular velocity omega radian per second. Therefore, the velocity of B, that is Vb, is known in magnitude and direction. The slider reciprocates along with line of stroke AO. The velocity of slider A, that is Va, may be determined by relative velocity method as discussed below. This shows in red color. First point, from any point O, draw vector OB in the second diagram. From any point O, draw vector OB parallel to the direction of VB or perpendicular to OB such that OB equal to VB equal to omega R to some suitable scale. Then second point, since AB is rigid link, therefore the velocity of A relative to B is perpendicular to AB. Now draw vector BA perpendicular to AB to represent the velocity of A with respect to B, that is VAB. Third point, from O, draw vector OA parallel to path of motion of the slider A, that is in x direction, which is AO only. The vector BA and OA intersect at point A. Now OA represents the vector of slider A, that is VA. The angular velocity of connecting rod AB, that is omega AB equal to VBA by AB equal to AB by AB anti-clockwise about A. The direction of vector AB or BA determines the sense of omega AB, which shows that it is anti-clockwise. Note, the absolute velocity of any other point E on the connecting rod AB may also be found out by dividing vector BA such that BE by BA equal to BE by BA. This is done by drawing line BA1 equal to length of BA mark BE1 equal to BE, join OA1. From E1, draw line E1E parallel to OA1. The vector OE now represents the velocity of E, and vector A represents the velocity of E with respect to A. Next, rubbing of velocity at a pin joint. The link in the mechanism are mostly connected by means of pin joint. The rubbing velocity is defined as the algebraic sum between the angular velocities of two links which are connected by pin joint multiplied by radius of the pin. Consider two links OA and OB connected by a pin joint O. Omega 1 is angular velocity of link OA or the angular velocity of point A with respect to O. Omega 2 is angular velocity of the link OB or the angular velocity of the point with respect to O. And R is radius of pin. According to definition, rubbing velocity at the pin joint O equal to omega 1 minus omega 2 multiplied by R if the link move in same direction, or omega 1 plus omega 2 into R if the link moves in opposite direction. Here is the diagram for link connected by pin joint in right side. Note, when the pin connect one siding member and other turning member, the angular velocity of the siding member is 0 because this slides. In such case, rubbing velocity at pin joint is omega R, where omega is angular velocity of turning member and R is radius of pin. तो ये बोल रहा है सेकेंड केस में ऐसा बता रहा है कि जब आपका एक पिन जॉइंट के दोनों तरफ अलग अलग चीज़ें जुड़ी हों, ठीक है, जैसे एक में साइडिंग मेंबर जुड़ा हुआ हो और दूसरे में टर्निंग मेंबर जुड़ा हुआ हो, ठीक है, तो स्लाइडिंग वाले में एंगुलर वेलोसिटी नहीं होगा, क्योंकि जो टर्निंग वाला होगा उसी पर होगा. सो द एंगुलर वेलोसिटी ऑफ टर्निंग मेंबर ओमेगा लिया, उसका रेडियस ऑफ पिन आर लिया. सो रबिंग वेलोसिटी ऑफ द पिन जॉइंट इज ओमेगा आर जब एक साइड आपका टर्निंग मेंबर जुड़ा हुआ हो और दूसरे साइड आपका साइडिंग मेंबर जुड़ा हुआ हो. आइए हम लोग एक एग्जांपल बनाते हैं. इन अ 4 बार चेन ABCD, ये ABCD 4 बार चेन है. AD इज फिक्स्ड एंड इज 150 mm लॉन्ग. AD यहाँ पर फिक्स रखा हुआ है बेस वाला और 150 mm लॉन्ग है. द क्रैंक AB इज 40 mm लॉन्ग एंड रोटेट्स एट 120 RPM क्लॉकवाइज. AB सबसे छोटा है 40 mm का और वो घूम रहा है, ठीक है, क्रैंक है 120 RPM क्लॉकवाइज में. वाइल द लिंक CD इज 80 mm and oscillates about D. BC and AD are equal length. BC और AD आपको 150 का है बोल रहा है. Find the angular velocity of link CD when angle BAD equal to 60 degree. ये स्टार्टिंग में इसने एंगल भी बता दिया हुआ है. BAD ए पे जो एंगल है वो 60 डिग्री बना हुआ है. गिवन डाटा आपके NBA इज 120 RPM, that is omega BA equal to 2 pi n by 60. So this is 12.568 radian per second. Since the length of crank AB 40 mm 0.04 meter, therefore velocity of B with respect to A or velocity of B, because A is fixed, A आपका फिक्स है तो B बस का निकलेगा. So that is VBA equal to VB equal to omega BA into AB. That is 12.568 into 0.04 AB. So this comes 0.503 meter per second is VBA. Here first space diagram created in left side and the right side vector diagram has been created. We have to create the vector diagram. First of all, draw the space diagram to the some suitable scale. तो इनको सबको suitable scale में लेकर space diagram बनाया. AD, DC, CB, AB ये बनाया पहले. Now the vector diagram is drawn as discussed below. यहाँ पर जो AB में VB है, V की वेलोसिटी उसके हिसाब से बनाएंगे. Now the velocity diagram, first point, since link AD is fixed, यहाँ पर क्या है, link AD आपका फिक्स है. Therefore point A and D are taken as one point in the velocity diagram. तो velocity diagram में A और D दोनों फिक्स है, इसलिए यहाँ पर वेक्टर डायग्राम में लेफ्ट कॉर्नर पर AD दोनों को एक ही जगह पर ले लिया क्योंकि वो फिक्स है दोनों. ठीक है. ड्रा वेक्टर AB परपेंडिकुलर टू BA. AB perpendicular to BA. To some suitable scale. To present the velocity of B with respect to A or simply velocity of B, VBA or VB such that vector AB equal to VBA equal to VB equal to 0.503 मीटर पर सेकेंड. ये हमको VB निकल गया 0.503. सेकेंड पॉइंट, नाउ फ्रॉम पॉइंट B ड्रा वेक्टर BC परपेंडिकुलर टू CB. फ्रॉम B वेक्टर BC परपेंडिकुलर टू CB. Okay. To represent the velocity of C with respect to B, that is VCB, and from point D, draw vector BC perpendicular to CB, with the velocity of C with respect to B, VCB, and from point D, draw vector DC perpendicular to CD, to represent velocity of C with respect to D or simply velocity of C, that is VCD equal to VC. The vector BC and DC intersect at C. By measurement, we find that VCD, that is VC equal to DC equal to 0.385 meter per second. We know CD equal to 80 mm 0.08 meter. So angular velocity of link CD equal to omega CD by VCD by CD, that is 0.385 by 0.08. So this comes 4.8 radian per second clockwise about D. This is the angular velocity. Fine. Next we will solve one more numerical. The crank and connecting rod of a theoretical steam engine are 0.5 meter and 2 meter long respectively. The crank makes 180 rpm in the clockwise direction when it has turned 45 degree from the inner dead center position. Determine first velocity of piston, second angular velocity of connecting rod, third velocity of point E, on connecting rod 1.5 meter. From the gudgeon pin. 4 point velocity of rubbing at the pin of crankshaft, crank and crosshead when the diameter of their pin are 50 mm, 60 mm and 30 mm respectively. 5th point, position and linear velocity of any point G on connecting rod which has at least velocity relative to crankshaft. These we have to calculate. Here the data given are NBO equal to 180 RPM or omega BO equal to 18.852 radian per second. Since the crank length 0.5 meter OB, therefore linear velocity of B with respect to O or velocity of B because of fixed point VBO equal to VB equal to omega BO into OB equal to 18.852 into 0.5 equal to 9.426 meter per second. Next point, first point, velocity of piston we have to calculate. First of all, draw the space diagram to some suitable scale as shown in figure 7.8a. Left side is 7.58a. Second point, from first point, draw vector AB perpendicular to BO to some suitable scale to represent velocity of B with respect to O or velocity of B such that vector OB equal to VBO, VB equal to 9.426 meter per second. From point B, draw vector BP perpendicular to BP to represent velocity of P with respect to B, that is VPB, and point O, draw vector OP parallel to PO to represent velocity of P with respect to O, that is VPO or simply VP. The vector BP and OP intersect at point P. By measurement, we find the velocity of piston P, VP equal to vector OP equal to 8.15 meter per second. Second point, angular velocity connecting rod. From the velocity diagram, we find that velocity of P with respect to B, VPB equal to vector BP. Here, vector BP equal to 6.8 meter per second. Since the length of connecting rod PB is 2 meter, therefore angular velocity of connecting rod omega PB equal to VPB by PB equal to 6.8 by 2 equal to 3.4 radian per second anticlockwise. Third point, velocity of point E on connecting rod. The velocity of point E on connecting rod 1.5 meter from the gudgeon pin PE equal to 1.5 meter, PE 1.5 meter is determined by dividing the vector BP at E in the same ratio as E divides PB in figure 7.8a. This is done in similar way as discussed in article 7.6 join OE. The vector OE represents the velocity of E. By measurement, we find that velocity of E, VE equal to vector OE equal to 8.5 meter per second. The point E on vector BP may also be obtained as follows: BE by BP equal to BE by BP or BE equal to BE by BP into BP. Next, velocity of rubbing. We know that the diameter of crankshaft pin at O, DO equal to 50 mm, that is 0.05 meter. Diameter of crank pin at B, DB equal to 60 mm, 0.06 meter, and the diameter of crosshead pin DC equal to 30 mm 0.03 meter, we know that velocity of rubbing at pin of crankshaft equal to dO by 2 into omega BO, that is equal to 0.05 by 2 into 18.85, that comes 0.47 meter per second. Velocity of rubbing at pin of crank, that is dB by 2 omega BO omega PP. So this is 0.06 by 2 multiply 18.85 plus 3.4. So this comes 0.6675 meter per second, because omega BO is clockwise and omega PP is anti-clockwise. And velocity of rubbing at pin of crosshead equal to DC by 2 into omega PB 0.03 by 2 into 3.4, 0.051 meter per second, because at the crosshead the cider does not rotate and only the connecting rod has angular motion. Position of linear velocity of point G on connecting rod, which has the least value relative to crankshaft. The position of point G on the connecting rod, which has the least velocity relative to crankshaft, is determined by drawing perpendicular to O from O to vector BP. Since the length of OG will be at least, therefore the point G represents the required position of G on the connecting rod. By measurement, we find that vector BG equal to 5 meter per second. The position of point G on the connecting rod is obtained as follows: BG by BP equal to BG by BP, BG equal to BG by BP into BP. So this comes 1.47 meter. And by measurement, we find that the linear velocity of point G, VG equal to vector OG, that is 8 meter per second.